Okay, these are the notes for AP Calculus on the topic of improper intervals when you have vertical asymptotes in the interval. So normally, normal definite intervals are computed on a continuous interval. But sometimes you might have a vertical asymptote either at the end point of the interval or somewhere in the middle of the interval. So let's take a look. Here's the graph of f of x. You can see visually what we're finding. 1 over the square root of 1 minus x squared. Notice there's nothing to the right of 1 or to the left of negative 1, because those would give you imaginary numbers that make it a negative inside the square root. So it only is continuous from negative 1 to 1, and even negative 1 to 1 squared give you 0 in the denominator, so it's undefined. Those create 1 over 0 vertical asymptote. In this case, notice we're going from negative 1 to 0, and negative 1, there's actually a vertical asymptote. So we'll draw that in here on our graph. You don't have to draw these to be able to compute them, but just so you can understand what we're trying to compute here. We've got this vertical asymptote right here. There's another one here, positive one, but that's not in our interval. So we're just going from negative 1 there to 0 right here. So we're looking at this area right in here. And notice, since it's going up to, this vertical asymptote heads up to, the graph goes up to infinity, the limit as x approaches negative 1 from the right is infinite. Sometimes this converges on a specific number here, even though it's infinite. Sometimes it just goes to infinity and diverges. So, if it's at the end point, you can start it off like you normally would and integrate. You just got to keep in mind that sometimes these will not converge on a specific value. So 1 over the square root of 1 minus x squared. Well, you might think use substitution, but if you say u equal to the function inside 1 minus x squared, the derivative is going to be negative 2x, and notice there's no x up here to cancel out with that. So really it's just a matter of recognizing 1 over the square root of 1 minus x squared. Does that look familiar? Well, remember that involves one of our derivative formulas. That's actually the derivative of arc sine of x. So when you find the antiderivative of this, it's going to give you back arc sine evaluated from negative 1 to 0. And then you substitute in the upper limit 0, so arc sine of 0 minus substituting negative 1 arc sine of negative 1. So remember, arc sine is evaluated. We restrict its range, so it's actually a function that only gives you one output. Remember, arc sine is evaluated between negative pi over 2 and pi over 2. So just in the first and fourth quadrants there in that interval. Otherwise, you would get more than one value out if you don't restrict it. So arc sine of 0, well, there's no triangle to draw there. You can see right here, sine is 0, the y coordinate. So that's just the angle 0. So this takes 0 and gives you back the angle 0. Minus arc sine of negative 1. Well, this is like negative 1 over 1. This is saying, remember, sine is the opposite over hypotenuse. Negative 1 over 1. But we can draw a triangle that has the opposite hypotenuse of negative 1, 1. I was just thinking about that. That's an impossible triangle there. So that's your clue. Okay, we can't draw the triangle. That means if it exists, it has to be at one of these points right on the axis. And where sine is negative 1, notice this is right here, at negative pi over 2. So this is minus negative pi over 2. You take the value of negative 1, and it gives you back the angle of negative pi over 2. And then the negatives cancel out, giving you a positive answer, which is what you would expect. because you can see this area here is above the x-axis. So this is an example of one that does converge. We got a specific value. All right, let's take a look at another one. So here the vertical asymptote was at the end point there. Now on this one, a little bit different. Again, you can try use substitution here. You could even factor this. The factors into x minus 1 and x minus 1. You could write 1 over x minus 1 squared, which will be helpful. Dx, but notice here we've got a vertical asymptote at 1, which you can see on the graph. It looks like this here. If you can see the square, just keep it in positive. So we've got a vertical asymptote right here. And it's not at the end point of our intervals, 0 or 3, it's somewhere in between those. In this case, at 1. So we can draw that in there. So vertical asymptote at x equals 1. And we're going from 0 to 3. So 0 is right here, 3 is right here. So we're trying to find this area right here, up until the vertical asymptote, and this area right here after the vertical asymptote. And to see if those converge on a specific number or are they infinite. So here, because the vertical asymptote is right in the middle of the interval, we can't just evaluate it as a single integral. That will oftentimes give us the wrong answer. So we actually have to split it up right at that vertical asymptote. So the first one would be from 0 to 1. And then you can rewrite this to make it a little simpler. X minus 1 to the negative 2. Plus, from the vertical asymptote to the upper limit, from 1 to 3. X minus 2 to the negative 2 dx. All right, so let's see what we get here now when we integrate each of these. So when you integrate this one, you get x minus 1 to the negative 1. We can use the u substitution shortcut on both of these. Over negative 1. From 0 to 1. Plus, same thing on this one. X minus, so actually axing over to 2 here. X minus 1 to the negative 1. Again, the shortcut, the derivative of the x minus 1 is just 1, so it wouldn't change anything with the substitution, divided by negative 1. From 1 to 3. And you can simplify it a little bit. You can pull out the negative, and then you'd be just left with, if you get rid of the negative exponent, 1 over x minus 1. Same thing here, you can pull out the negative out in front. So, if we substitute in now, got negative, and when you substitute in 1, and notice we get 0 on the number, 1 over 0, and then minus, when you substitute in 0, you get negative 1, minus, substitute in 3, you get 1/2, minus, substitute in 1 here, you get So you can see in this case, this one is going to be undefined, as is this one. So because those are undefined there, we can't compute the limit there. And because of that, this one diverges. All right, so let's take a look at a couple without the graph now. Oh, one thing to notice, if you had not split it up on this one, if we had just integrated and gotten x to the -1 to the -1 over -1, evaluated from 0 to 3, it would have actually given us the wrong answer. We would have got -1 here. Then you'd plug in, this would be 1 over x minus 1, you'd get 1/2. Minus, you plug in 0, you get -1. And you can see that would actually give you an actual answer here. It would be incorrect. All right, so just be careful of those ones with the interval, vertical asymptote in the interval. Make sure you split it into two separate ones. Sometimes these actually do exist, but not in this particular problem. Sometimes they do converge, but it does require you splitting it into two. All right, the next one here. This one, notice the thing that makes it undefined is 4, which is on the very end of the interval, so we don't need to split it up here. But there's a vertical asymptote 4, so keep in mind this one might diverge. So this one, if we just pull out the 2 here, out in front, the constant, and then the integral from 0 to 4, and then we just rewrite this as x minus 4. Notice it's the square root cube, that's to the 3x, but it's to the negative 3x, since it's on the denominator. And then dx. Again, we can just use the shortcut for u substitution, since the derivative of x minus 4 would just be 1. So you can just use the power rule and get x minus 4, add 1 to the exponent, so it would be -1/2. Dividing by -1/2 is the same as multiplying by the reciprocal, which is -2. From 0 to 4. Then you can pull out the -2 along with the 2, gives you -4. And if we switch this to radical form, it'd be 1 over the square root of x minus 4 from 0 to 4. Then we've got -4. And when you plug in 4, notice we get 1 over the square root of 0, which is 0, minus, and you plug in 0, we get 1 over square root of -4, which is imaginary. So in this case, you can see there's 2 reasons why. Just this alone would be showing it's divergent. In this case, you also have an imaginary number there. So both of those shows you this diverges. All right, let's take a look at the next one here. This one, notice, goes from -1 to 1. But notice, if you set the denominator equal 0, 0 makes the denominator 0, so there's a vertical asymptote. Even though we don't have the graph, we can tell there's a vertical asymptote at x equals 0, but that would give you 4 over 0. So again, we've got to split it into 2 intervals, like we did the second one. -1 to 0. Plus Then you can pull out the 4 on this one. And then rewrite it as just x to the 2/3 of the number, x to the negative 2/3. Again, you can pull out the 4 here. And again, rewrite it as x to the negative 2/3. So the integral is going to look very similar when you split it up like this. Just different lower and upper limits. And now let's integrate each one. So we've got 4 on the outside on this one. When you integrate x to the negative 2/3, add 1 to the x one, that's adding 3/3, gives you x to the positive 1/3. And then dividing by 1/3 is the same as multiplying by 3. And then this one again, we've got a 4 on the outside. You get the same thing when you integrate. Add 1 gives you x to the 1/3 divided by 1/3 times 3. You got the same antiderivative, just different numbers to substitute in. And both of these you can pull out the 3 as well to make it simpler. So now you've got 12 on the outside. And if you switch this to radical form, that'd just be the cube root of x. And same thing here, 12 on the outside. And the cube root of x. So then you can substitute in, you get 12. Cube root of 0 is 0, minus cube root of negative 1, negative 1. Plus 12. Cube root of 1 is 1, minus cube root of 0 is 0. So you get 12, this becomes positive 1, so that's 12 plus 12 times 1 is 12, so we get 24. So this one does converge because we get a specific number. And that concludes the notes for AP Calculus on the topic of improper integrals with vertical asymptotes.